Okay, good morning, everyone. My name is Chenhui Huang from the NEC Corporation, Japan. Here, I'd like to introduce my researcher. I will talk about an application that using an IMU sensor embedded into the shoes to measure the physical condition of the human. Here is the outline of my research. And here is the background. Daily assessment of mobility is important because the declining of mobility is a long-term and gradual process which directly connected with the four risks. For prevention, we need to know the condition of the mobility every day. Conventionally, mobility is evaluated by the time up and go test. Here showed for TUG. Its metric is the time of finishing TUG. Shorter time means stronger mobility. It can reflect the three parts of ability, including sit to stand, straight way walking, and turning. There was already conventional technology that conventional wearable technology aimed to monitoring the mobility in the daily living. The first type, they focus on identifying the motion during the TUG test. TUG test every motion. This requires this type of system requires the users to make effort to regularly access the TUG tester app and do the TUG by themselves every day. Second type, they focus on the nature walking and assist to stand movement from hours of daily activity from data. However, this type of system required a very big amount of data, wireless transmissions and computation, make it too hard to saving power on the wearable sensor. Okay. Our technology and our system address the three technical issues on the wearable sensor system. The first, comfortable wearing. The second, easy to use, such as less battery charging. And the third, high precision model for the prediction. For the first issue, we propose to use our previously developed in-shoe motion sensor like this. It can be embedded into an insole and inserted into the shoes. It measures the foot motion, and it will be very easy and comfortable to wear because everyone need to wear a shoes. And it can be inserted any shoes the user like. For the second issue, the lightweight model for less power consumption is needed. To achieve that, we proposed a model that use only single stride natural straight walking to estimate the mobility and use multivariate linear regression for model construction. For the third issue, we propose to determine novel predictors from the foot motion, which is measured by this IMS, to raising the model precision. Here is the detail of our device. It can be inserted into the insoles, and it is the contents of the inside the sensor box. It included an IMU, microcomputers, memory, real-time clocks, and some circuits to control it. It only driven by a 3-voltage coin battery, and with our previously power-saving algorithm, IMS can be finished all the calculations and all the predictions using one stride foot motion on the edge device. I'm sorry that I cannot show you the detail of the algorithm here, and you can refer our previous published study on the IEEE sensor journal. It makes the IMS possible to achieve the measurement of daily living for 1 year without battery charging in some use cases. For such type of IMS sensor, we already have a product on sale. Yes. Here is a brief introduction of our idea how to construct the model with high precision. Specific lower limb muscles during sit to stand, turning motion in TUG are associated with the straight gait motion during one gait cycle. So we considered that we can determine some significant predictors from the special gait phases from the foot motion. For example, quadriceps is the performance of a quadriceps correlated with the sit to stand motion, like this. There was also correlated with the gait motions during this phase marked as orange blocks during the gait according to the biomechanical knowledge. By our previously developed SPM loss-of-loss algorithm, we explore new predictors from foot motions and selected the optimal predictors for model construction. Maybe you want to say that, so you can easily assume that the people with a faster gait speed should have high mobility. So why you want to explore such a lot of predictors to do the model? So the answer is partly right, but not exactly. I will explain in the discussion part at last. So in the experiment, in this study, we collected data from two groups of elderly subjects, including 62 for model construction and 46 for model test. Considering the sex difference in gait, we respectively constructed a model for male and female subject. In the experiment, we connected foot motions where the subject will ask for walking on the 6 meters straight path for 4 trails at a comfortable speed. And each subject was conduct the TUG test once. Then we process the data to obtain the 4 categories of the data as input of our SPM loss-of-loss algorithm, including individual physical attributes such as age, BMI, and 20 types of the stride, 20 types of strides of temporal spatial gait parameters, and the strides of foot motion waveform and the target variable TUG. Here is the result. I will show the result on the left side that we selected from the temporal spatial gait parameters. Here, for both sexes, maximum speed in one stride was selected, which suggested that the gait speed indeed significant for mobility estimation. That's right. However, other gait parameters were also selected. For these numbers, I'm sorry that I can't details, and it is listed in my IEEE Sensor Letters paper. You can refer that. And we also discovered some new predictors from the foot motion signals in frontal and the horizontal plane, shows as the color blocks on the right side, which means this part of foot motion was very important for the predictions. This is very interesting because that human walking straight also always walking straight along to the sagittal plane. However, there was many predictors from the foot motion in horizontal and the frontal plane. So this can be, which suggested that these predictors is correlated with the turning motion or sit to stand motion. And here is the result of the model test, model evaluation and test. We use the intraclass correlation coefficient and mean absolute error, adjust the R-square to evaluate the models. Here is the agreement plotted by the LIB1 subject out class validation. It achieved excellent ICC agreement and very high, very low MAE around 0.4 second and high R-square values. As a test model, we use the Bland and the Altman plot to test the model. There were 3 out of 6 male and 31 of 39 females, totally 75.6% subjects in group test group inside the interval of limited of agreement, which determined by the train model, which suggested that our model has a very well individual robustness. And here I would like to discuss whether only gait speed can estimate the mobility well. Here in the left panel, I will use the only gait speed, and here I use the maximum gait speed in one stride to regress the TUG. Compared to the optimal predictor sets showed before, for both sexes, they only achieve very worse SCC agreement and twice worse MAEs and much lower R-squares. They suggested that only gait speed cannot represent the mobility well, and because there was still C2 standard and turning ability were included in the TUG. And for high precision predictors determined from foot motion signals were inevitable. We can know from this study. Here is my conclusion. In this study, we discovered significant predictors for mobility from foot motion signals in frontal and horizontal planes. And we successfully constructed a mobility estimation model with high precision using one stride foot motion obtained from an IMS and tested its effectiveness. And in the future work, we will test the validity in a very long time cohort study. And we will construct the 4 risk prediction models by the result in this study. At last, we would like to thank Dr. Koji Fujita from Tokyo Medical and Dental University and Dr. Yoshitaka Kobayashi from the National Institute of Advanced Industrial Science and Technology for kindly providing partial test data in this study. Thank you for your attention.